So yes, as you say, the topic is a more uniform Friedberg-Muchnik theorem. Now, it is an interesting topic, I think, for this crowd or anyone, because what we're going to do is a sort of, you could call it reverse mathematics. In fact, people often call this reverse recursion theory. We're going to explore theorems from recursion theory from the point of view of fragments of piano arithmetic. And maybe that's a topic for this slide or the next. But if we begin by looking at a bit of background on the theorem itself, the Friedberg-Muchnik theorem is the first theorem really in recursion theory that uses what's called the finite injury priority method. So we'll see what that means in a moment, but I will mention that Friedberg and Muchnick both proved this theorem independently of one another in the late 1950s. Friedberg was an American and Muchnick was in the Soviet Union, and that's why it was possible for them both to prove the theorem. I believe Muchnick was a little earlier, in fact. And what it says is that there are two sets of natural numbers, A and B, that are recursively enumerable. That is, they can be enumerated one by a Turing machine, but they are Turing independent of one another. That's what that notation with the T means. That is, there's no Turing machine that using the one set as the oracle can compute the other. And that holds for both directions. Now, this is known by the following two results to be, as far as piano arithmetic is concerned, it's provable from B sigma 1 plus the totality of the exponential function, plus the basic axioms about semi-rings starting at 0 and going up. But let's see, in the early 1980s, Simpson proved without publishing, and in the late 1980s, Mitilianos, who was a student of Slayman, proved with publishing that the conventional proof of this theorem that both Friedberg and Muchnick came up with can be carried out using only I sigma 1, that is, induction applied to recursively enumerable subsets of the natural numbers. And it wasn't that much longer after that publication of Mitilianos that Chong and Murat, who I believe were in Singapore at the time, came up with a completely different proof for models of not I sigma 1, which uses, we'll see it later on, or a version of it, which uses certain features of these models. I want to call them non-standard models, but it's the axioms which are non-standard. And those give us certain special functions we can grab onto. It's actually pretty fun. Sort of impossible function. Hold on. There we go.
Why is plus x in brackets here?
Because in the notes I based these slides off, I just assume x all the time.
Mm-hmm.
That's just my own private notation. I forget x.
If I may add something, Leszek here, the Chong-Murat's paper is actually a bit sloppy about x. I mean, they do need it essentially for their argument, but they never fully acknowledge it. So it's a bit confusing when you read the actual paper.
Yeah, that might be the origin of my bad habit. I'm not sure at this point why I often assume x. But anyway, our contribution today is nothing too crazy. I'm going to give a simplified account of Chong and Murat's proof, which it sounds like Leszek could do as well. And a more uniform proof that produces not one pair, but two pairs, A1 and B1, and A2 and B2, one of which satisfies the theorem. Now, when I set out to prepare these slides, I was certain I had a method that gives you one single pair, but in the course of preparing them, I've become a bit more cautious about that, let's say. So we'll do the safe thing and give you 2 pairs. And the general, some people call this general sort of doing things reverse recursion theory. So I'll give you a bit of a sloppy motivation for it. Maybe overselling it a bit, I hope not. But when you study fragments of piano arithmetic, you have a lot of nice and powerful techniques for making models or proof theoretic techniques or whatever. And these theories of I sigma 1, B sigma n, and so on are all well studied. The relationship, the linear relationship between them is well known. And that they have something to do with zero jump, zero double jump, and so on is also well known. Now, what I'm going to claim right now is that the study of fragments of piano arithmetic could always use more examples. And I know there are plenty of examples of things that are equivalent to I sigma n, maybe from sort of a computer science standpoint or something else. But one thing that you could always use is some actual inductive arguments that do use these levels of induction. And those can be found at least up to a certain n, maybe 3 or 4. These can be found really explicitly in existing theorems in recursion theory. And on the other hand, recursion theorists, whether it's out of pedagogical considerations or just liking to classify things, do classify their own arguments in terms of zero jump trees, zero double jump trees. And there are a few other methods for recursively enumerable constructions. There have been attempts, in fact, to categorize these arguments as sigma 1, sigma 2, delta 2, delta 3. But if you want to be rigorous about it, sometimes finding a reversal, as in reverse mathematics, using that point of view, this point of view, can actually give you a satisfying answer to those questions. Now, mind you, sometimes you don't get the answer you were expecting, but anyway, that's the motivation I'm claiming for today. That we can understand induction by looking at recursion theoretic constructions, and vice versa, that we can understand these recursion theoretic theorems ideally a little bit better by looking at them explicitly in these models of restricted pieces of piano arithmetic. Now this slide is more about notation than anything else, because I'm going to be drawing a bunch more pictures like this. In order to visualize an oracle construction from one set to another, we'll just draw them both looking like big or semi-infinite Turing machine tapes, where, say, the set of even numbers starting at 0 looks like 1, 0, 1, 0, 1, 0. And then to take that set and compute something else from it. Well, to compute a whole set of numbers, really, a whole set of yes or no questions. Each of those computations will use some finite part of the oracle tape. In this case, we have some sort of computation. It's left unspecified, but to compute that 0 is indeed a member of B, it uses those first 3 elements of A. 0 is not in, 0 is in, 1 is not in, and 2 is in. And that's all that's required. And as you keep computing more yes or no questions for membership to B, you use bigger and bigger initial segments. And this is how it's going to be drawn. So to compute whether the 4th element, 3, is in B, you use 9 elements of A, or 9 possible elements of A. I like to call that an initial segment of the set. So the initial segment of A of size 9 And when you actually try and formalize this in arithmetic, we're going to elide over all the details, but this is what it looks like. F is an initial segment, so it's a sequence of 9 zeros and 1s. B is number 3, and then I in this case is 0, indicating that 3 is not in B, based on this sequence of zeros and 1s being in A. That's not going to be important in the future. It's just if you're wondering how it was made technical. And there's a further wrinkle to it. When our theories get weaker and we're talking about RE degrees, it can cause problems to talk about initial segments of a set, just because it won't actually be a finite set with a code in the model sometimes. It'll be something like a proper cut, which we'll worry about a bit later. But the solution in that case is, instead of talking about initial segments, to talk about two finite pieces of positive information and negative information that don't necessarily have to add up to an initial segment. And that's what our computations will be based on in that case. And now I'm just going to draw, using the same kind of picture as before, where to decide a given number in the computed set, you use some finite piece and there's an arrow pointing to its uppermost extent. Just an idea of how you would prove the Friedberg-Muchnik theorem by the original proof. And we're going to leave out all the details, but it will go like this.
May I interrupt you at this point with a question? So if you formalize it, the statement of Friedberg-Muchnik theorem naturally, what would be the arithmetical complexity of this statement?
That is well, let's see, for all Turing machines, there are two Turing machines computing A and B.
No, they are just constant, so probably. For every possible reduction, there is an error. So it's for every exists an error, and being an error is probably P1, yeah? Or P2.
Probably the sets A and B are somehow will be somehow explicitly given to us, right? So
yes, that's what I'm thinking.
It's not an existence. So, okay, A and B are given.
In the statement it's existent, but in the proof it's not. So we prove it with. But when we say that there is a reduction has an error point in some type, in some specified type, I think the specified point is that either it's P1, I think. So it means that it's either it belongs to one set and there is no computation that proves that it's in the other set, which is a P1 statement, or vice versa. There is a There is a computation that is never found to be inconsistent.
Well, the way I would look at it is, if you fix both A and B beforehand,
yes,
for every Turing machine in both directions, so that's a leading for all statement, there exists a point where it's wrong. And that being wrong is something like sigma 2, I guess?
I think we can say that there exists a point with additional information of what type of the error and what are the computation positively involved in this error. and then it's only one universal quantifier, that there is no negative things, which the negative results will never destroy this thing.
It's definitely pi3 if you fix A and B, the whole statement. A and B are not reducible to one another is pi3, and then at least over B sigma 1, I think you will have the question whether you can actually fix A and B. You will get A and B, I think, explicitly from the traditional proof, but not necessarily over if you don't have I sigma 1. Because you rely heavily on the function violating sigma 1 induction, which might come out of the blue.
Yeah, I agree with that estimate at least, where if you fix them beforehand, it should be pi3, but forgive me, I haven't thought about that complexity lately, if at all.
Okay.
Perhaps by the end, I'll have had time to review.
We'll see. Okay, very good. Okay, go on, please. Sorry.
But here's how the structure goes. For a given, we call it diagonalization. For a given Turing machine, number 1 in this case, we pick a witness, W1. And our goal is to make it so that, in this case, B doesn't compute A at exactly that one point given by the witness. And the way I've drawn it here, we've already found a computation that with B, as it is so far, computes a value for what A should be at that point. And when we see that, we lock down something we're familiar with now, I guess. We lock down part of B so that it doesn't change again, namely those first 3 elements. And then we change A, in this case by enumerating an element into it, that W1, so that, well, I guess depending on whether the computation said W1 was supposed to be an A or not, we either enumerate to make it wrong, or we don't enumerate to keep it wrong. And we just sort of go on, blindly going forward, finding witnesses as appropriate that respect these requirements, and then waiting for a computation that converges at one of those witnesses. In this case, I wrote W8, and it converges with using only the first 7 many of A, which, depending how you set it up, probably won't be actually possible. But if you imagine you can choose such a witness, then, and if this happens, once again, we set up a restraint on A this time, so that that initial segment of A doesn't change, and we diagonalize that spot W8. And there's only one wrinkle to this construction. It is that we place a priority ordering on these requirements, that the nth Turing machine doesn't compute the one set from the other. And in this case, 1 has the highest priority, that W1, but number 8 is about 7 levels below it. So that if we encounter a new computation that seems to go below the restraint for that witness W8, for something of intermediate priority or better priority than 8, that one is allowed to cancel W8, like so, and place its own new restraint. And we continue in this way. Now, there could be something below W5, or W8 could come back, respecting its new spot on the pecking order, its lower priority, and get a new witness somewhere else and set up a new restraint and continue. But as far as we're concerned, when it comes to I sigma 1, I sigma 2, we really want to look at the verification for this. And as you can see, or as I think you can see, W1 is guaranteed to be satisfied, or the requirement associated with W1 is guaranteed to be satisfied because either it does act at some point, in which case the diagonalization is set up, and since no other requirement has a bigger priority or a better priority, let's say, than W1, it stays forever. If, on the other hand, it doesn't act, that's because there was no computation to diagonalize against, and we're also okay. And then looking at the second requirement, after the stage W1 has stopped acting forever, the same argument applies. And the point is, for us, this is a sigma 1 event, and therefore sigma 1 induction is enough to guarantee that it works forever. And the theorem in the end is proved. Now here is sigma 1, or excuse me, I sigma 1 itself. I phrased it in the regular sets, or the bounded sigma 1 sets formulation. In fact, I've put a little unusual phrasing on it. Instead of calling the numbers finite or coded, I called it computable. But as long as we're working over B sigma 1, those things are the same. A computable finite set is a delta 1 finite set, is a delta 1 bounded set. Now, if you want to know what a non-finite set that's bounded is, or a non-computable set that's bounded is, you can look at, in any non-standard model, just a cut, such as omega. That's the true natural numbers. And there's a mistake on this slide. I've called a cut a set containing 0 enclosed under successor. It's also intended that they not have any holes in them, so they're closed downwards. But anyway. For models of B sigma 1, here there's no brackets for the exponential. The negation of I sigma 1 is equivalent to the statement that there is a sigma 1 cofinal function mapping such a cut, a sigma 1 proper cut, cofinally into the model, which is called M. And that's not really, it's not hard to prove. What it is very useful. I mean, I would call it very useful. I guess the slide contradicts me right here. What it really is ruinous to that proof of Friedberg-Muchnik, because such a function f will completely destroy the argument. The basic reason is that I sigma 1 was supposed to get you through all those requirements, guaranteeing one by one that they either act or don't act, and you go all the way through the model M that way. But with this kind of ruinous function, you could get stuck inside one of those proper cuts infinitely many times, or unboundedly many times, injuring requirements of lower priority. And that ruins the argument. On the other hand, I was calling it useful, and it is, because this sort of forbidden, ruinous function f can actually itself be used. And that's the argument of Chong and Murad for proving the Friedberg-Muchnik theorem. Now, this is where I'm going to go into, in a way, a little bit more detail, rather than those funny pictures, as if they, I don't know if the pictures are the best way of presenting the Friedberg-Muchnik theorem, but here they're just totally impossible. So we're going to do it with words and symbols and this lemma. So you will remember that way back close to the beginning, there were two ways of formalizing the Turing machines, the Turing functionals. One of them used finite initial segments of the oracle tape. And one of them just used finite pieces of positive and negative information. Here below I sigma 1 is where that second version becomes really important when we're looking at RE sets. And the first lemma is that the positive part of the information really isn't needed when we're using Turing functionals on RE sets. And I'll just go back a bit to cut it off. The reason for that lemma being true is simple. It's that when you have an RE set and a Turing functional, you can always take the Turing machine defining that set and sort of fold it into the Turing functional as a subroutine, we could call it. So that it doesn't really need to consult the positive part of the oracle to see whether something is in the set B. It can just wait for those elements to go in and see if they go in. But the negative part of the information is necessary. Now here's how the proof goes, if you're ready. To prove the theorem, we enumerate elements both into A and B, because they're RE sets, that's normal. And at the same time, we also enumerate elements into the complements, A bar and B bar. Now, mind you, we don't enumerate the whole complement, but we do put things permanently into the complements. And that is to serve as a version of the restrictions we had before for the diagonalizations. The purpose is to diagonalize. And that main tool that we were calling ruinous before, the very useful function f, is what's at the bottom here. We start out by chopping up the natural numbers, which are a non-standard model n, into pieces based on that f. And there's some assumption on f growing very, very fast. The exact speed at which it grows isn't really important right now. We can compute it at the end if you want. But it's, to be safe, we'll say it's something like 3 exponentials stacked together. It's nothing crazy, but it's enough to make everything fit. And making everything fit is the theme of this theorem and its proof. And it's my version of the proof. It's shorter and I hope more understandable than the original, but well, anyway, it fits on a slide. So here's how it goes. The first 4 lines or so are just a repetition from before. And now it's a stage-by-stage construction. And the interesting thing about this argument, or one of them, is that unlike usual recursion theoretic constructions, it doesn't go stage by stage, one by one through the natural numbers. It goes one stage for every element of that proper cut I. And the actions of these stages are spread out according to the codomain, the range of that function f. And at each of these stages S, we do many things in a sequence. So I've called them phase 1 and phase 2. Phase 1 is some kind of looping behavior. And then phase 2 is just a finishing move to round off the round. So phase 1 works like this. You have less than S, this very big number, growing with this very fast growing function. And below S, you look for all, I call them unsatisfied E. What I mean is the requirements that haven't been diagonalized yet among the first E many Turing machines. And we look for an available A, one that hasn't been put into the set A or its complement yet, such that the computation deciding A seems to have halted, using B as an oracle, while using less than half of the available elements of each of these intervals we've chopped up the natural numbers into. So it's not something I'm able to draw a picture of very well, but remember we've chopped the natural numbers that are serving for b into all these proper cut many intervals, each of them much bigger than the last. And if there is a computation which uses less than half the available b's in each of the intervals bigger than where we are now, and there's a few different indices here, so remember I is back up at stage s equals f of 2i. So that's where that index comes from. And if that's the case, we make this computation permanent, at least we hope permanent, by adding these elements to the complement of b, the oracle, and diagonalizing by adding a to the set it's not supposed to be in. And then we go back to the first of these three steps, or these three bullet points in phase one, and look for another E and another A. And we repeat this until no more such pairs are available. And eliding some details, as long as F is fast enough growing, this will not run into any obstacles. We will eventually run out of E's and A's, those pairs. And at that point, we've reached a step where any computation of that sort that does converge uses at least more than half of the available b's in one of those intervals. And if that happens, we go to phase two, and we just add 1/2 of the available elements of each interval to b rather than b complement. And if you want to be safe, say 1/2 of the available ones plus 1. The intention is that by the pigeonhole principle, each of those negative pieces of information, which was supposed to be part of the computation, is going to intersect with the positive information we're adding to b, making those computations not true. They're not used in computing A from B. And that's really the whole argument, or at least the whole construction.
Okay, so we can do it for all this phase two thing we can do because I is a proper cut, so it is somehow finite from the point of view of M or something like that. Is it what is meant here?
Well, even if it were a standard model and you'd cut up the natural numbers into some number of pieces, as long as they were size bigger than 1, you could add 1/2 of the available elements to each of them.
Are we supposed to do it in, let's say, finitely many steps in the sense of M or not? I'm somehow confused here. So is it an external construction or is it construction?
Just a more basic question. If we are just naive, completely naive, this is not a proof of Muchnick-Friedberg theorem for standard recursion theory. Just it's a proof only in special model where something is false, and so we do not get any normal proof in this way. Yeah,
you're right. This proof will not work.
Of course.
And the reason is that it's only because f is very fast growing that you can do phase one as many times as you like without running out of space. So each time you do that, you take away up to 1/2 of all the available elements from each interval. So you can only do that logarithm many times. But we want to do it, well, we're setting it up in such a way that that isn't really an obstacle.
Okay, about f and the fast growth of f. My understanding was that, so from negation of I sigma, so let's just check the understanding of basic setup, because that's what important, the details come next, so to say. But so we have not I sigma 1, so we have this model of not I sigma 1, therefore we have this cofinal function mapping RE function, sigma 1 function mapping f mapping I to cofinally to m. And then you claim that f has to grow faster than exponent.
Much faster.
Much faster.
So we can worry about exactly how fast, if you like.
So is it so that we can always select such an f, so that we can ensure that f grows sufficiently fast in this way for any cut? So
yes, yes, that can be done.
So you can select the cut I in such a way that such an f will also be fast growing, something like this. You shorten the cut sufficiently.
Well, if you had just some cut and some f, all you have to do to make it faster growing is define g equals 2 to the 2 to the 2 to the f of x. Something like that.
Ah, okay. So
it will always be fast.
Not too fast. So it's just a few levels of exponent faster. It's not like it's next Grigorchik class or something like that.
No, it's nothing crazy. It's just enough to make the argument work.
Okay, okay, good. That's that was one point of worry. Still, I think a few comments about the setup of this argument is needed here. So, okay. So what are you defining? So by this construction, you define these A and B. These sets A and B is essentially two Turing machines. Two codes of these are E sets A and B. Is that what you?
Yes, they're two recursively.
So essentially, what we are dealing here with, we have two, let's say, two sigma 1 definitions of sets A and B inside this model M, and these sigma 1 definitions are uniform in the sense that they're the same in each model. Once you fix these, so they're defined uniformly in M in some sense. Okay.
Yes, using F, they're defined.
Using F. Once you fix F, and F is fixed by the assumption, so F is given by another sigma 1 definition. So then you proceed to define A and B by this algorithm. And I'm only worrying about this phase 2 where you define. So you extend the domain of, so you extend the, let's say the set B by infinitely many, by adding to it infinitely many elements, right?
Yes, I see. So, yeah, if you don't want to add infinitely many things at once,
well, I'm used to the idea that RE definitions add things in finite steps, so to say, by adding finitely many.
Yeah, if you want, you can say, remember for later, before you use those higher JIs, JJs, remember you have to add half the elements.
Okay.
That will, it's
so
more
you can sort of
complicated to write down.
Spread it to further steps, for further iterations of this procedure with phase 1 and phase 2.
Yeah.
So okay, good. Then
Push it on down the line if you like, but it has to be done.
okay.
And then you can, most of the verification for this construction is built in. There may be a few small worries. As you say, figure out how fast f has to grow, but that falls out of the construction itself. And then you also have to check that every individual e does eventually get an a. And that verification goes through with b sigma 1. The big worry is that when you're doing this phase 1 and phase 2, I suppose, you're only messing with things for j greater than or equal to I. But b sigma 1 ensures that any computation that eventually might contrapositively compute the one set from the other, it does so after a finite amount of time. And that, then you get your contrapositive or contradiction or whatever you want to call it. It's almost enough to fit on a slide, only a few details. Important though they may be. Now here's a second construction, a third construction, similar to the first, which will lead into the final fourth construction. We're back to these pictures of Turing machine tapes with arrows going between them. I don't know if I should apologize for that or if you're relieved, but here's how blocking proofs work. Instead of going back and forth one by one, choosing these witnesses and performing these diagonalizations, it's sometimes useful to, I've stopped putting W labels in now, to lock down a computation from B to A. But when you do that, to use that size of that computation or some other size falling out dynamically from the construction, to rearrange the priorities of the requirements. So in this case, I've somewhat arbitrarily taken that number 3 that falls out of the first diagonalization, and I've given 3 requirements going the other way, all the same priority. Instead of one by one back and forth, they have first 1 going this way, then 3 going the other way. And then, let's see, what is this number? 1, 2, 3. I think it's 8. So we could have up to 8 things going the opposite direction. I've left out all injury this time. And then I've only drawn 2, but there are about 15 or so, maybe 13 requirements, minus those 3, leaving 10, all of the same priority going in the other direction again. Now, the same kind of induction argument will show that if you set it up this way, the way I've described, if you write it down nicely, this will still work. It's a bit funny, but it also has some advantages, especially in working in non-standard models of piano arithmetic fragments, or in what's called alpha recursion theory. It also is useful. But it's not so useful that you get a better amount of induction required. It actually, this argument uses the same amount of induction. But it has one nice feature. If you try and carry out this construction and it doesn't work, there is a first block. I'm calling these blocks from 0 to 3, and then up to 8, I believe it was, and up to 13. These are each called blocks. And these, of course, have get bigger and bigger with non-standard length in general. But if the proof doesn't work, what that ends up meaning is that there is one block that acts cofinally often, a first block, and looking at the way the requirements act on that block, the way the diagonalizations go, there will only be finite or up to finitely many of those diagonalizations, but structurally they'll occur as a proper cut. And the destinations of those arrows will point up cofinally through the model M. And this turns out to be exactly the sort of function that was required for Chong and Murad's proof. So here's a more uniform proof of the Friedberg-Muchnik theorem. Working in a model of B sigma 1 plus X, we can construct two different pairs of RE sets, one of which is guaranteed to satisfy the theorem. And we don't use the original proof, but we use the blocking version of it, which is almost the same, but which has this feature that if it fails, it will give us a nice F, or a terrible F, depending on your point of view, which can then be used exactly as Chong and Murad's strategy, but with a little more guessing, a little more uncertainty about what the actual value of F is. Because of course, if we're in a model of I sigma 1, there is no F. And even if we're not in a model of I sigma 1, we might not ever actually know what that minimal block was that doesn't, that acts cofinally often. But if we keep changing our mind and changing our guesses as to what that F was supposed to be, or which block was supposed to produce that F, in the limit, we can indeed carry out that proof. So that either the blocking strategy worked or it didn't. And it gave us the F, and we were able to carry out a version of Chong and Murad's proof. And that is all I have for today. I mentioned when I set out to prepare these slides, I thought I had a better proof that only gave one pair, but I became more skeptical in the course of preparing them, and I'm confident enough in my skepticism, I'll just call it a question. Is there a really uniform proof for this theorem? Anyway, that is all I had to say today. I'll give you one good reference for this sort of reverse recursion theory type of thing. It's, again, the same Chong and Li Wei and Yang Yue, all three at the National University of Singapore, wrote a good survey for the Bulletin of Symbolic Logic. That's all.
Okay. Thank you. May I ask the first question, then I will give the opportunity for others. Of course, it's interesting to make more specific what is meant here by uniformity of proof. But what if you simply, well, let's say, suppose you are inside intuitionistic arithmetic, something like intuitionistic B sigma 1 plus X. Would any of these arguments give us a proof of Friedberg-Muchnik in this context or not?
I haven't spent much time with intuitionistic systems, Heiting arithmetic or anything like that. But what I expect is that the way it's proved is we don't know which one works. So
yeah, so that indicates somehow that this is not constructive, right? So that's exactly what presumably should make it fail in intuitionistic B sigma 1 plus X, but maybe it's exactly what you are after in studying this question, so to say.
Yeah, but even if you did have a single pair and you had two different reasons
yes,
for it
yes,
to work,
yes,
maybe
of course.
that wouldn't work either, right?
Yeah. One thing is to have one pair, and another thing is to have to be able to do it correctly. Okay, maybe others will have more questions. Please.
So I have a very stupid question, but I don't know. Maybe so. I didn't know anything about non-standard models, but I guess that your third proof with blocking is just as a proof of alternative proof of Friedberg-Muchnik theorem in standard sense, in standard recursion theory. Is it true?
Yes, I mean, they would look at you funny if you proved it with blocking, because normally you don't need it, but it works just fine in the standard.
Okay, but can you just explain again this proof, just for plain people without any models? What are you doing compared to standard proof, or just kind of?
Yeah, so I'll even go back to this.
Yeah.
This picture here. So if you were doing it with blocking here,
yeah,
in the standard proof, you have sort of a priority ordering, 1, 2, 3, 4, 5, 6, going down in priority.
Yeah.
And then when you set up this restraint here, you move your witnesses on B. That's the effect setting up the restraint has.
So if we are satisfying the requirement number n, then all future requirements may be completely restarted at that point.
Yes,
and standard proof.
And so on.
And now, what you do instead of this?
Now, it's the same, except instead of the future requirements being, or the lower priority requirements being n plus 2, n plus 1, n plus 2, and so on, you actually change the priority ordering during the construction.
Okay, so how do we do this?
In this case, we would have, say, 1 going down, and then 2 going up, 3 going down, 4 going up to start. After the first one is acted, we put the next 3 together.
Maybe you can change the picture on your slide to illustrate what you are saying, so to say. You had this picture at the end of your talk where you with this blocking.
If you prefer. So I don't know if this is a good picture or not, but what it's trying to communicate is that after the first one is acted and it's set up a restraint of 3, then the next 3 requirements going the other way are all equally strong. They're equal priority. So even number 2 going downwards is of lower priority than those 3.
And they, if something have equal priorities, they never interfere with each other. We don't need to decide which is more important.
Right, because at least in this argument, they're always going the same way. So the only worry is that they'll have the same witness, that is where the arrow is coming from. But we make sure that doesn't happen. All they do is add a restraint to A. And they otherwise don't interfere with each other on B. So there's no competition between them.
Yeah, so if the requirements go in the same direction and they use different places, then we can consider them as a group.
That's right. Except because it's a sigma 1 event, whether they act or not. So by requirement, they're a group, but they don't necessarily act at the same time.
And so if they act, if one of them act at some moment, then what do we do with the others?
They stay. They could still act later.
But the priority is not changed, or what?
Their priorities are not changed.
And what is changed then? So what is the so at some stages of the construction, we have the kind of classification into all the requirements into priority classes numbered by integers, or what? How it works?
Yeah, you can number them by integers. So depending.
So we have the most important requirement going, say, from A to B, and several requirements going from B to A, which are less important, and several requirements going from A to B, which are even less important. So we have this groups of requirements, yeah?
That's correct, yes.
Yeah, and so what is, imagine that one of the requirement in one of the groups acts. So what then you do then?
Right, so say this one with 3 requirements, I drew them all as acting at the same time, but that's not necessary.
Yeah.
It could be one acts, then the other ones stay dormant for a long time and other things happen. But then the other 2 act, or one of the other 2 acts. And
no, but what happens with priorities? Imagine one acts. Does it mean that what do we shift and what we restart? How it works?
Well, in this case, we have, let's say, 2 groups. The first one with just one element going down, and then the second group.
Yeah.
So that second group can act 3 times. Every time it acts, it doesn't affect these first 2 groups, but it will affect all the others.
But will not affect their priorities. They will just be of the same priority level, but just they restart later with later elements. Yeah.
No, it'll also move that red line further up, so it will actually affect the priorities of the third group every time this acts. It will make that third group bigger and bigger.
No, priority is I think that the threshold is different from the priority. The priority means that which requirements are taken into account, and who wins if who is destroyed when somebody acts.
Yes,
it's
that's true.
Not exactly the line. So the priority order is changed or not?
The priority order is changed. Now, you're right, that is true. What I'm doing is I'm making those 2 numbers the same, because having fewer indices, fewer numbers lying around is always good. But you're right, it's serving 2 different purposes here. One is as the restraint on A, but it's also the size of the block for the priorities. 2 different purposes for the same number.
Okay, so sorry for that. Maybe if somebody understands like Lova, he can explain me later. But I am confused completely. But don't worry.
Well, we have a text where this is. We have a text where it is written down.
You know, text is okay, but if you can explain it to me, it will be even better. Not now, just in general. Yeah. Okay.
Can I ask a question?
Yes, please.
So you made these 2 pairs of sets. What does the wrong pair look like?
It depends. Let's see what happens. What are the 2 pairs of sets? One of them is built. So if the blocking strategy fails, what it has is a proper cut in one of the sides, and the other one should be computable. It has not a proper cut, but a bounded, non-finite sigma 1 set. So it has something with the Turing degree of a proper cut, and the other side is computable because it's getting these infinitely big, cofinally big restraints.
And do you know which is which in
No,
that case?
it could go either way.
Okay.
And if the other side fails, let's see. I guess they're both computable because they'll probably both run out of witnesses. If I'm not mistaken. Either they run out of witnesses or you can reconstruct the halting problem pretty easily just by looking at whether they act after a certain point. So
that would be bad if one of them produces the halting problem.
Right.
If you wanted to join it together into one pair.
In any case, these are the obstacles these are the first obstacles you'll encounter trying to get a single pair A and B. Because at first you try and just put them together, but for this reason it doesn't work.
Okay, yeah, great. Thank you.
Okay.
I ask something, or do we have to finish?
No, you can ask.
Just a quick question. So, David, in the I sigma 1 proof, if I understand correctly, A1 and B1 are actually concrete indices, right? They're fixed standard numbers giving you Turing machines. Here, are A2 and B2 also fixed numbers, or do they actually depend on where A1 and B1 fail? So do you actually get two concrete pairs of numbers, or is that not the case?
You'll get indices for Turing machines. So
4 indices for Turing machines?
Yes.
Okay, that's interesting. Thanks.
Okay. Anyway, it's a peculiar situation with this Friedberg-Muchnik theorem, I think. Maybe the ideal would be to have a completely normal proof without this dichotomy built into it, so to say. That would be, of course, maybe that's possible. I mean, a proof in B sigma 1 plus X.
So you mean that there is a chance that standard, you just invent some new proof of Friedberg-Muchnik in terms of ordinary recursion theory, but this new proof turns out to be more easy to formalize without this.
Of course. That's now, in a sense, the combination of so the main result that we heard today was that we do have a proof in B sigma 1 plus X of this theorem, but it is strangely non-uniform. So it is a kind of merger of two proofs, one in a true theory like I sigma 1 and another in a false theory like not I sigma 1. This not I sigma 1 proof is it's a peculiar situation. We don't normally prove mathematical results in this way by assuming that induction holds or induction fails. In a sense, this is a very peculiar thing. So probably the guess is that if one thinks longer about it, make a completely normal, so to say, down to earth, understandable proof without models will be available. But
or one can explain from some formal viewpoint why Friedberg-Muchnik is really needs some more difficult and serious tool than other theorems of recursion theory. If this it's kind of miracle, what is this priority argument, why it's really needed, and how can we formalize what it means that theorem use some priority argument.
But there were, I may be wrong, but were there any, there were some methods related to alternative proofs of Friedberg-Muchnik using, or at least solutions to post problem using these equivalence relations and fixed points techniques, things like that. I forgot who was this, Kuchera, not Kuchera. There were some alternatives, priority-free arguments for construct incomparable degrees.
Yeah, there was a Kuchera argument, but yes, it was not clear formally what does it mean to be priority-free, and And also there are many other results which imply this. For example, there is this low sets for Kolmogorov complexity, and there is some kind of argument which is not exactly the priority argument, but still even more, maybe more complicated. But
but maybe they need to be analyzed from the point of view of reverse mathematics as well. What is, maybe they're worse than Friedberg-Muchnik proof, but who knows?
I don't know offhand of analysis of the cost function argument or anything like that. Do you, Paul?
Oh, sorry.
Nope. Okay.
Sorry.
Okay. If there are no further questions, then maybe we have to thank our speaker. And yeah, thank you, David.